Welcome to Hidden Dangers Lurking Within Our Solar System. I'm your narrator, and today we're going to explore the cosmic threats that could reshape life as we know it, and how humanity's unique resilience might just be our salvation. Before we begin, take a moment to hit that subscribe button and ring the notification bell. Your support helps this channel continue bringing you these deep dives into humanity's cosmic future. When humans first gazed up at the night sky, they saw beauty and mystery. The twinkling stars, the wandering planets, the occasional comet streaking across the darkness, all of it filled our ancestors with wonder. But as our understanding of the cosmos has grown, so too has our awareness of the dangers that lurk in the seemingly peaceful void surrounding our fragile blue world. The solar system, our cosmic neighborhood, is not the serene, stable environment we once imagined. It's a dynamic, chaotic place filled with objects that move, collide, erupt, and explode. From the scorching surface of Mercury to the frozen wastes beyond Neptune, hidden dangers await the unwary. But here's the thing about humans. We don't just cower in the face of cosmic threats. We study them. We understand them. And eventually, we find ways to overcome them. Today, we're going to explore the hidden dangers lurking within our solar system, not to frighten, but to understand. Because in understanding lies our greatest strength. The same ingenuity that took us from primitive tools to space stations will be what saves us from the cosmic threats that await. Let's start close to home with the threats that could quite literally hit us where we live. Near-Earth objects, or NEOs, are asteroids and comets that orbit the Sun and come uncomfortably close to Earth's orbit. The dinosaurs learned about this threat the hard way when a 10-kilometer asteroid slammed into what is now the Yucatan Peninsula 65 million years ago. The impact released energy equivalent to 10 billion Hiroshima bombs, creating a global catastrophe that wiped out 75% of all species on Earth. But unlike the dinosaurs, we have something they didn't: a big brain and the technology to use it. We've identified over 28,000 NEOs to date, including more than 2,000 potentially hazardous asteroids that could cause regional or global devastation if they struck Earth. Take Apophis, for example. When this 370-meter asteroid was discovered in 2004, initial calculations suggested a 2.7% chance of impact in 2029. Slim odds, perhaps, but astronomically high when planetary destruction is on the line. Fortunately, refined observations have ruled out an impact in 2029, though Apophis will still pass close enough to be visible to the naked eye, the first asteroid of its size in recorded history to come so near. But it's not just asteroids we need to worry about. Comets, those icy wanderers from the outer solar system, can also pose a threat. They move faster than asteroids, giving us less warning time, and their trajectories are harder to predict due to outgassing as they approach the Sun. And then there are interstellar objects, visitors from beyond our solar system. In 2017, we spotted Oumuamua, the first confirmed interstellar object to pass through our system. 2 years later came 2I/Borisov, an interstellar comet. These objects remind us that threats can come not just from our own cosmic backyard, but from the vast interstellar wilderness beyond. Sun, giver of light, heat, and life, is also a temperamental star capable of unleashing devastating energy upon our technological civilization. Solar flares are sudden releases of energy from the Sun's surface that can emit as much energy as 1 billion hydrogen bombs. When directed at Earth, they can disrupt radio communications and satellite operations. Even more concerning are coronal mass ejections, CMEs, massive bursts of solar wind and magnetic fields that can trigger geomagnetic storms when they hit Earth's magnetosphere. The most powerful geomagnetic storm on record, the Carrington event of 1859, caused telegraph systems to fail across Europe and North America, with some telegraph operators reporting sparks flying from their equipment. If a Carrington-level event happened today, it could cause widespread blackouts, disable satellites, and disrupt everything from GPS navigation to internet service. The economic impact could reach into the trillions of dollars, and recovery might take years. And we've had close calls. In July 2012, a CME comparable to the Carrington event missed Earth by just 1 week of orbital position. Had it hit us, we would still be recovering from the damage. Humans have only been spacefaring for about 65 years, but we've already managed to create a significant hazard in Earth orbit: space junk. There are currently over 34,000 pieces of debris larger than 10 centimeters orbiting Earth, along with millions of smaller pieces. Each one travels at speeds of up to 28,000 kilometers per hour, fast enough that even a paint fleck can damage a spacecraft. The International Space Station has had to perform emergency maneuvers multiple times to avoid collision with debris. And in 2009, we witnessed the first accidental hypervelocity collision between two intact satellites, which created thousands of new pieces of debris. This raises the specter of Kessler Syndrome, a scenario where the density of objects in low Earth orbit becomes high enough that collisions between objects could cause a cascade of collisions, rendering space activities and the use of satellites in specific orbital ranges impractical for generations. As we continue to launch satellites at an unprecedented rate, particularly large constellations like Starlink, the risk of triggering this syndrome grows. And if it happens, we could find ourselves effectively trapped on Earth, cut off from the very space infrastructure we've come to depend on. If you're finding this exploration of cosmic dangers fascinating, take a moment to hit that like button. It helps more people discover this content, and I'd love to hear your thoughts in the comments. What cosmic threat do you find most concerning? Let me know below. Earth isn't the only world in our solar system with active volcanoes. In fact, some of our planetary neighbors make Earth's volcanoes look like campfires in comparison. Take Io, Jupiter's innermost large moon. Caught in a gravitational tug-of-war between Jupiter and the other Galilean moons, Io is the most volcanically active body in our solar system. Its surface is dotted with hundreds of active volcanoes that spew plumes of sulfur and sulfur dioxide up to 500 kilometers high. Some of these eruptions are so powerful that they've been observed from Earth. For any future human outpost on Io, perhaps mining its rich mineral resources, these volcanoes would pose a constant threat. Eruptions could bury facilities under lava flows or toxic sulfur deposits, while the radiation from Jupiter would add another layer of danger. Back on Earth, we face the threat of supervolcanoes, massive volcanic eruptions that can eject more than 1,000 cubic kilometers of material and cause global climate effects. The Yellowstone caldera, the Lake Toba supervolcano in Indonesia, and the Taupo volcanic zone in New Zealand are all capable of such eruptions. A supervolcanic eruption could lower global temperatures by several degrees for years, causing worldwide crop failures and famine. The Toba eruption, 74,000 years ago, may have reduced the human population to just a few thousand individuals, a genetic bottleneck from which we're still recovering. The atmospheres of other planets in our solar system hold their own unique dangers. Venus, often called Earth's sister planet due to its similar size and mass, has an atmosphere that's a testament to a runaway greenhouse effect. Its atmosphere is 96% carbon dioxide, with surface pressures 92 times that of Earth, equivalent to being 900 meters underwater. The surface temperature averages 462 degSC, hot enough to melt lead. Any human mission to Venus would have to contend not just with the crushing pressure and extreme heat, but also with clouds of sulfuric acid that would corrode most materials we might use for habitats or protective suits. Mars, seemingly more hospitable, has its own atmospheric hazards. The red planet is prone to dust storms that can engulf the entire planet, blocking sunlight and covering solar panels with dust. In 2018, Such a storm ended the mission of NASA's Opportunity rover when its solar panels couldn't generate enough power to keep it operational. For future Martian colonists, these storms could pose serious threats to power generation, visibility, and even the integrity of habitats if fine dust particles manage to work their way into seals and mechanical systems. Beyond the inner solar system, the gas and ice giants present environments so extreme they challenge our very definition of habitable. Jupiter, the largest planet in our system, has a gravitational pull 2.5 times stronger than Earth's. Its atmosphere consists mainly of hydrogen and helium, with wind speeds reaching up to 620 kilometers per hour. As you descend into Jupiter's atmosphere, the pressure increases to millions of times that at Earth's surface, eventually reaching a point where hydrogen becomes metallic. Saturn, Uranus, and Neptune present similar challenges, with extreme pressures, temperatures, and wind speeds that would crush, freeze, or tear apart any conventional human habitat. Even their moons, some of which might harbor subsurface oceans that could potentially support life, present extreme challenges. Europa, for instance, has a surface temperature of about 160 dECC and is bathed in Jupiter's intense radiation. For humans to establish any kind of presence in these outer reaches of our solar system, we would need to develop technologies far beyond our current capabilities. Pressure-resistant habitats, radiation shielding, and energy sources that can function in the absence of significant solar power. I hope you're enjoying this journey through our solar system's hidden dangers. If you are, please consider subscribing to the channel for more deep dives into humanity's cosmic future. And don't forget to share this video with someone who might find it fascinating. Knowledge is always better when shared. Faced with these cosmic threats, humanity has not remained idle. We've developed increasingly sophisticated systems to detect and monitor potential dangers. For near-Earth objects, we have programs like NASA's Center for Near-Earth Object Studies, CMEs, and the Catalina Sky Survey, which scan the skies for asteroids and comets that might pose a threat. The Pan-STARRS telescopes in Hawaii can detect objects as small as 300 meters across at the distance of the Moon. But our detection capabilities still have significant gaps. We've identified only about 40% of objects larger than 140 meters that could potentially impact Earth. And smaller objects, while less globally catastrophic, could still cause significant regional damage if they hit populated areas. That's why projects like the upcoming NEO Surveyor mission are so important. This space-based infrared telescope, scheduled for launch in 2026, will be able to spot asteroids that are currently difficult to detect because they approach from the direction of the Sun. For solar threats, we have a network of satellites monitoring our star. The Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, provide continuous observation of the Sun, while missions like Parker's Solar Probe venture closer to the Sun than any spacecraft before, gathering data that helps us understand and predict solar activity. The Space Weather Prediction Center issues alerts and warnings about potential solar events that might affect Earth, giving satellite operators and power grid managers time to take protective measures. As for orbital debris, the U.S. Space Surveillance Network tracks objects as small as 10 centimeters in low Earth orbit and 1 meter in geostationary orbit. This information is shared with satellite operators worldwide to help prevent collisions. But tracking isn't enough. We need to start cleaning up the mess we've made. Various concepts for debris removal are being developed, from harpoons and nets to capture large pieces, to lasers that could nudge smaller debris into lower orbits, where they'll eventually burn up in the atmosphere. Detection is only half the battle. Once we identify a threat, we need ways to mitigate it. For asteroids on collision courses with Earth, several deflection strategies have been proposed. The simplest is the kinetic impactor approach, essentially ramming a spacecraft into the asteroid to alter its trajectory. NASA's Double Asteroid Redirection Test, DART, successfully demonstrated this technique in 2022 when it intentionally crashed into Dimorphos, the moonlet of asteroid Didymus, changing its orbital period by 32 minutes. For larger asteroids, or those detected with less lead time, we might need more powerful approaches. A gravity tractor, a spacecraft that hovers near an asteroid using its own gravitational pull to gradually alter the asteroid's path, could work for smaller objects given enough time. And in truly desperate circumstances, we might resort to nuclear devices, not to blow the asteroid apart, which could create multiple impacts instead of one, but to create a standoff explosion that would vaporize part of the surface, creating a thrust effect that changes the asteroid's trajectory. For solar threats, our options are more limited. We can't stop a CME from happening, but we can prepare our infrastructure to better withstand its effects. This includes hardening power grids against electromagnetic pulses, designing satellites with radiation-resistant components, and maintaining backup systems that can quickly replace damaged infrastructure. Some researchers have even proposed a massive magnetic shield at the L1 Lagrange point between Earth and the Sun, which could deflect charged particles from CMEs away from our planet. While currently beyond our technological capabilities, such a shield represents the kind of ambitious thinking we'll need to protect our civilization as it becomes increasingly dependent on vulnerable electronic systems. Beyond detection and mitigation, we're developing technologies that would allow humans to adapt to the harsh environments of other worlds in our solar system. Radiation shielding is a critical area of research. Future spacecraft and habitats will need to protect their occupants from both solar radiation and galactic cosmic rays. Approaches range from water-filled walls, water being an excellent radiation shield, to magnetic fields that mimic Earth's magnetosphere. For Mars missions, NASA is developing the Mars Oxygen in Situ Resource Utilization Experiment, MOX, which extracts oxygen from the Martian atmosphere. This technology could provide breathable air for astronauts and oxidizer for rocket fuel, reducing the amount of supplies that need to be brought from Earth. Self-sustaining habitats that can recycle water, grow food, and generate power will be essential for long-duration missions or permanent settlements. The Biosphere 2 experiment in the early 1900s, despite its challenges, provided valuable insights into the complexities of creating closed ecological systems. I think using local materials could allow settlers to construct habitats and tools without having to bring everything from Earth. Researchers are already experimenting with simulated lunar and Martian soil to determine what kinds of structures could be built on these worlds. And for the extreme environments of the outer solar system, we're developing robotic explorers that can withstand intense pressures, temperatures, and radiation. The proposed Dragonfly mission to Saturn's moon Titan, for example, will use a nuclear-powered drone to explore this world, with its methane lakes and organic-rich atmosphere. The question for you all: which of these adaptation technologies do you find most promising for humanity's future in space? Drop your thoughts in the comments below. I read every single one and love hearing your perspectives. As we look to establish a permanent human presence beyond Earth, the dangers we've discussed present significant challenges, but also opportunities. Long-term survival in space will require us to develop closed-loop life support systems that can function reliably for years or decades. The International Space Station, which recycles about 90% of its water but still requires regular resupply missions, shows both the progress we've made and the distance we still have to go. Protecting colonists from radiation will be particularly challenging on worlds without magnetic fields or thick atmospheres. Mars colonists might need to build habitats underground or shield them with several meters of soil. On airless worlds like the Moon, habitats might be built in lava tubes that provide natural radiation shielding. Interplanetary infrastructure, communication networks, navigation systems, supply chains will need to be robust enough to withstand solar storms. micrometeoroid impacts, and the extreme environments of space. Redundancy will be key, with multiple systems capable of performing critical functions if primary systems fail. The psychological challenges of living in isolated, confined environments far from Earth should not be underestimated. Studies of Antarctic research stations and submarine crews provide some insights, but a Mars colony or asteroid mining operation would face unique stressors. Despite these challenges, the potential benefits of space colonization are enormous. Beyond ensuring the long-term survival of our species, space settlements could access vast resources, from metals in asteroids to helium-3 in lunar soil, potentially solving resource scarcity issues on Earth. The technologies we develop to overcome these challenges won't just help us in space, they'll transform life here on Earth as well. Imagine cities that recycle water and waste with the efficiency of a space habitat, or power grids hardened against solar storms that never lose electricity during natural disasters. This is the paradox of space exploration. By preparing to leave Earth, we develop the very technologies that might save it. The technologies we develop to address cosmic threats will have applications far beyond their original purpose. Advanced warning systems for asteroids and solar storms will drive improvements in sensor technology, data processing, and predictive modeling. These capabilities could help us better predict and respond to natural disasters on Earth, from hurricanes to earthquakes. The energy systems designed for space habitats, efficient solar panels, compact nuclear reactors, advanced batteries, could help solve Earth's energy challenges, reducing our dependence on fossil fuels and mitigating climate change. Life support technologies that recycle water and waste, grow food in confined spaces, and maintain healthy air quality could be applied to create more sustainable cities on Earth, particularly in harsh environments like deserts or Arctic regions. And perhaps most ambitiously, we might eventually develop the capability for cosmic engineering, deliberately altering the environments of other worlds to make them more habitable for Earth life. This concept, known as terraforming, remains speculative but represents the ultimate expression of humanity's ability to adapt hostile environments to our needs. Think about it. The same ingenuity that allows us to survive in the vacuum of space could help us build floating cities as sea levels rise, or create self-sustaining communities in Earth's most inhospitable regions. The technologies that protect astronauts from radiation could lead to breakthroughs in cancer treatment. The systems that recycle water and air in space habitats could revolutionize how we manage resources in water-scarce regions. This is the hidden promise within the dangers we face. Necessity drives innovation, and the harshest challenges often produce the most transformative solutions. Throughout our history, humans have faced countless threats to our survival, from ice ages and supervolcanoes to pandemics and nuclear weapons. Yet, we've persisted, adapting to changing conditions and developing technologies that transform dangers into opportunities. The cosmic threats we've discussed today are no different. They represent challenges, yes, but also catalysts for growth and innovation. They push us to expand our understanding, develop new technologies, and extend our reach beyond the cradle of Earth. Consider this. Every major advance in human history has come in response to some challenge or limitation. Agriculture developed in response to food scarcity. Medicine evolved to combat disease. The digital revolution arose partly from the need to process information more efficiently during wartime. Now we face challenges on a cosmic scale, and our responses will be equally transformative. The technologies we develop to detect asteroids, shield against radiation, and survive in hostile environments will reshape not just our future in space, but our lives on Earth as well. And unlike the dinosaurs, we won't simply wait for disaster to strike. We're actively searching for threats, developing countermeasures, and planning for contingencies. We're taking control of our cosmic destiny in a way no species before us ever could. This is what makes humans unique in the known universe. Not just our intelligence or our technology, but our resilience, our ability to face existential threats and emerge stronger. We don't just survive, we adapt, innovate, and ultimately thrive. The solar system is indeed filled with hidden dangers. Asteroids that could impact Earth, solar storms that could cripple our infrastructure, extreme environments that challenge our very existence. But these dangers exist alongside incredible opportunities. Resources beyond imagination, new frontiers to explore, and the potential for humanity to become a truly multi-planetary species. As we continue to explore and understand our cosmic neighborhood, we'll develop the technologies and capabilities needed not just to survive these threats, but to harness them for our benefit. The asteroid that might have destroyed us becomes a mining opportunity. The radiation that might have killed us drives advances in medicine and materials science. The extreme environment that might have been uninhabitable becomes our new frontier. This is the story of humanity, not just surviving in a dangerous universe, but thriving because of how we respond to those dangers. Our greatest strength isn't that we avoid challenges, but that we rise to meet them. The hidden dangers lurking within our solar system aren't just threats to be feared. They're opportunities to be seized, challenges to be overcome, and catalysts for the next great chapter in human history. And that, perhaps, is the most important lesson of all. In the face of cosmic danger, humanity doesn't cower. We explore, we innovate, we adapt, and ultimately, we prevail. Thank you for joining me on this journey through our solar system's hidden dangers. If you enjoyed this exploration, please hit that like button and subscribe to the channel for more deep dives into humanity's cosmic future. I'd love to hear your thoughts in the comments below. Which cosmic threat do you find most concerning? What technologies do you think will be most important for our survival beyond Earth? Or perhaps you have questions about aspects of these dangers we didn't cover in depth today. And if you found value in this video, please share it with someone who might appreciate this perspective on our place in the cosmos. Knowledge, like the universe itself, only grows when shared. Until next time, keep looking up, but always with a clear understanding of what's really out there.